So before we go further, let's look at an example problem. Example problems make you happy, right? Example problems make you feel good about yourself because this is your way of testing to make sure that you understand the material. And then in this example problem, we see D Tagatose undergoes a reaction in a basic solution. Two aldohexoses are made. What are they? So we need to take a look to see how this question is different and how it relates to the previous video of these sugars reacting in a basic environment. So first off, we've got to figure out what D Tagatose looks like. I mean, I can't answer this problem if I don't draw the structure of D Tagatose. And this is a structure that I don't want you to memorize, right? This was not one of the ones in the box that I told you that you should know. So this structure will be given, or you will have a chart and you can look up this structure and try to find it. So D Tagatose, if I find and when I find that structure, is CH2OH up here at the top, and then I see this carbon backbone with a CH2OH at the bottom. At this carbon we see a double bond O, and then at this carbon we see an OH on that side. So let me erase this, that's kind of confusing. So we see an OH over here and an H to the right. On this carbon we see OH to the left and H to the right. And then on that carbon I see OH to the right and H to the left. So that's the structure for D Tagatose, right? I've looked this up. This is something that I shouldn't memorize. This is something that I can always find, and that structure is going to be given. So there it is. And it says that this structure is going to undergo a reaction with a base. So we're going to add in here OH minus, and we want to know what would happen, what would form. Okay, so in the previous video we discussed this whole mechanism. I didn't give you the full story though, right? This is kind of part 2 in addendum. So I gave you part of the story, and we can use that kind of information to answer this part of the question as well. So with this example, this OH minus group can come in, pull the hydrogen off, and then put the hydrogen back on. And we could get two forms of the alpha carbon, right? Here's the alpha carbon. There's an alpha carbon right here. So we could end up with the same structure as before. So option number 1, we always can get the same structure. And this structure is D Tagatose. Alright, so this is number 1. But that's not really what the question wants, right? Because the question says two aldoses can be made. Well, if it makes D Tagatose all over again, this is not an aldose. This is a ketose. There's a ketone group there. So this is a ketose that I'm working with. So that's not really going to make any sense for me, right? So if I take the hydrogen off and put the hydrogen back on, this is one of the possibilities. However, it's not the possibility that the question wants, but it is true, D Tagatose could form. Okay, well, if the H doesn't go on that direction, it could go on the other side as well. So I can draw that option too. So CH2OH here, and then we get CH2OH here. A double bond is formed there, and then this OH group could flip sides, right? We can form an epimer. That's what we learned in our previous video. So this C2 epimer can be formed, and when hydrogen goes on, it can go on to the other side and sandwich to the left, and that forces OH to the right-hand side. Well, this is a different sugar. And this sugar I need to try to find in that chart that I'm given. So 1 carbon, 2 carbon, 3 carbon, 4 carbon, 5 carbon, 6 carbons. 6 carbons is that bottom line in the chart, and I see that the OH is right hand, left hand, right hand. So right hand, left hand, right hand. If I match that and try to find it, well, I'm going to find D sorbose as this name of that structure. Okay, that could form. right? That is another one of our options. So this is okay. This is true. That can work. However, D-sorbose, just like D Tagatose, these are ketoses because there's a ketone group here, right? So that's again not what the question wants. The question says what two aldohexoses are made. So now you're kind of scratching your head and you're thinking, okay, well, in the previous video, he told me that the hydroxide can come in, pull the hydrogen off, and I have two choices. Hydrogen can go back to where it came, or hydrogen can go on the opposite side. And this still happens. It still works, right? These are two of my options, but it's not the full story. There is another route that the mechanism can take. And this gives us some other opportunities to make more sugars. And what goes on is that this keto group can rearrange on me. And the reason is because, again, we're forming an enol functional group. So in this C double bond O, if this changes to a CO and a double bond here, and an H can go on to this oxygen, we have formed an enol. I'm not going to go through that mechanism. You can find that mechanism in the book if you want to take a look at it, but it's not something that I'm going to ask. But what I do ask is that you remember that with the ketones, this carbonyl can move. It is a gypsy, right? It doesn't have to stay in one location. So this carbonyl can move up to the top. The mechanism allows that to happen. If you want to know why that can happen, then take a look at the text. I'm not going to go into detail with it here, but that can take place. Alright, so if that happens, then what we can see is that this carbonyl moves up to the top, and now, ding ding ding, we get our aldose because we have a aldehyde. Okay, so we still have a carbon here that had an O group on it, and then we still have 1, 2, 3 other carbons. So 1, 2, and 3 other carbons. Now this OH group is at that location, this OH group is at that location, and this OH group is at that location. So because this carbonyl's moved up, it's now this carbon that is given the choice. Water can come in and protonate that oxygen, and then the H can follow suit on that side, or when that carbonyl moves up to the top, again, you've got a choice. This was my double bond O, and then we had 3 other carbons, right? This one went this one went right-handed. The next one went left-handed, and this one went right-handed. Well, hydrogen here, hydrogen there, hydrogen there. We chose to put the OH group to the right here, but I could easily, just as before, choose to put the OH group to the left, and this gives me my other choice. So this, ladies and gentlemen, is how we get a aldose, because that carbonyl can move. The carbonyl can move through that molecule to a neighboring carbon at least, and fluctuate between an aldose and a ketose. The same thing can happen if I start it with an aldose. We didn't mention it in the previous video, but that was an option route. If I start with an aldose, that can go to a ketose if it wants. If I start with a ketose, it can go to an aldose if it wants. As long as it's in a basic solution, this is what happens to the carbonyls. So now I need to go through and I need to find what these structures are going to be called, because I've identified 2 aldoses now that can come from it. So I flip to the aldose chart, and I need to look for an OH group that goes right hand, left hand, left hand, right hand. And then when I find that, right, left, left, right, this is called D galactose. So there is the first aldohexose that this rearrangement can make. And then if I look at this structure, this is a left, right, right. Kind of like the army march, right? Left, right, and this is D idose. Okay, so there's the story with the actual structure itself. And as far as, I'm sorry, I made a mistake. Let me go back. This structure, the carbonyl was here. This OH group was actually to the left-hand side. So that was actually here, which forces this to be a different sugar. So I apologize, I got a little carried away. See what carbohydrates do to me? They make me happy. So this OH group stays in position to the left. This OH group stays in position to the left. This one stays in position to the right. The one that changes is this one up here with the carbonyl. So now we need to look for one that is left, 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 right. And when I find the left, 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 right, then this is called D Tagatose. So those are the two aldohexoses that I can make with this reaction. Okay, so let me kind of sum up what this reaction's doing. If I have a sugar and I react it with a base, I can basically get the sugar again, or the C2 epimer of that sugar. The other route that can happen is that the sugar can rearrange on itself, and I can go from an aldose to a ketose or vice versa. And when this happens, I basically get two more C2 epimers. Okay, and that's exactly what we've done here in this example. I started with a ketose. Well, I showed you one route that gave you two possibilities. The ketone group stayed in position, and you basically got the reformation of the starting product, and you got the flip C2 epimer of that sugar. And the other option that we discussed just now, a couple of minutes ago, was this ketose forming an aldose. The carbonyl moved on me. And when that happened, you still get two possibilities. They are still C2 epimers, so you look and you find those structures that are in that chart. So there's the story, the full story now, with the what we're calling the base catalyzed epimerization and the base catalyzed enol-diol rearrangement, because this carbonyl is moving through the molecule. So 4 possibilities here. The question only wanted 2. It wanted only the aldo versions of the sugars that were made or that could be made, but you've got to keep in mind the other 2 possibilities are out there as well. It's not what the question wanted, but the other possibilities are out there. Okay, so in the next video, we are going to move on to our next reaction, and the next reaction is basically our oxidation reduction reactions. So we're going to be taking a look at what happens with my carbonyl bond and how can I force that carbonyl bond to change. What can it do? What kind of sugars can I get because of it? So congratulations, first reaction down. We move on to number 2 in the next round.